Welcome you all to the Research Spark YouTube channel. We are running to the course Analog and the Linear Electronic Circuit, and this is the last part of the Unit 2nd Introduction to Linear ICs. So here is the outline of our discussion. So here we'll see the open loop configurations, non-ideal effects in the operational amplifier, and the frequency response of the operational amplifier. So since we have already discussed the different types of the configurations in our previous sessions, so here mostly we are going to talk about the only practical configurations, not ideal one. So ideally, like we have discussed in the previous slides, previous discussions, so here we are going to talk the non-ideal effects in the operational amplifier mostly. So if you remember, we have already discussed in our previous session about the inverting amplifier, means inverting amplifiers. Let me give you the small ideas. So here actually if we are giving the inputs through the negative terminal, that is the inverting terminal, then outputs will be the shifted, phase will be shifted by the 180 degree, or simply that is why we are calling it as the inverting amplifier. So, in case of the the practical or ideal one, we have already got the gain that is equal to the minus R2 by R1, if you remember. But here, if you will calculate this, so let's find out the practical, that is the non-ideal effects again. So again here, the since no we know the we are going to use the I1 is equal to I2 techniques, because no current will allow to flow inside your operational amplifier because of the high resistance. And so the v1, the I1 is equal to I2, and you can find out the v out will be equal to the minus of AOL into v1. And in closed loop, mostly now since we are talking about the practical, so closed loop gain will be your equal to the v out by v1, and using the v1 that you have the found in the first equation. So from there you can use and get the values of the ACL, that will be equal to the minus of R2 by R1, that is the output voltage in case of open loop gain, and divided by V1, that will be equal to the 1 plus of 1 by AOL into 1 plus of R2 by R1. So this will give you the closed loop voltage gain. Similarly, here is the circuit for non-inverting amplifier. So again, we have already discussed it in the ideal one. So this is practical one. So again, you can find out the V1 and V2 and find out the gain. So V1 will be your V1 minus of V out by AOL, and close, and V out will be your AOL into V2 minus V1. V2 is actually the voltage that we are supplying here, and V1 will be same as the reflecting. Exactly, it will not be zero because this is not the ideal one, but you can consider it. You can find out the V1 and then find out. So V1 will be your V1 minus of V naught divided by AOL, and so finally your closed loop gain will be V out by V1, which will be equal to 1 plus R2 by R1 divided by 1 plus of 1 by AOL and 1 plus of R2 by R1. So from here you can find out the practical closed loop gain for the non-inverting. Now if AOL is very high, that you can just try, you can put, then you will get the closed loop gain will be the ideal closed loop, that it will be equal to 1 plus of R2 by R1, that we have already obtained in the previous session. So here actually AOL will be very high, but not the infinity. So you can use this equation closed loop, which will be equal to the 1 plus of R2 by R1 divided by 1 plus 1 divided by AOL into 1 plus R2 by R1. So now what are the major effects of the non-ideal parameters in the operational amplifier? So here are the summary, just check these summaries. So input voltage limits. First thing is that two input voltage limitations must be considered: a DC input voltage limit and a differential signal input voltage. All transistor in the input differential amplifier stage must be properly biased, so there is a limit in the range of the common mode input voltage and can be applied and still maintain the proper transistor bias. Output voltage limits, of course, it will depends on the DC power supply that we are supplying through the pin 4 and 7 in the operational amplifiers. It cannot be infinity as per ideal case. Output current limitations, the maximum current out of or into the operational amplifier is determined by the current rating of the output transistor. Practical operational amplifier circuits cannot source or sink an infinite amount of the current. And finite loop voltage gain, of course, finite loop voltage gain cannot be the infinity practically, but definitely it will be very high. So the non-ideal parameter value will affect circuit performance. Input resistance, ideally input resistance we are considering is infinite, but practically it will be the very high, but not infinite. So especially for BJT circuits, this parameter is one finite. Output resistance, ideally we are considering 0, but the which means there is no load effect at the output. In practice the value cannot be 0. Finite bandwidth, so ideally we are considering the operational amplifier, the voltage, the bandwidth is infinite. However, in practice the bandwidth is finite because of the capacitance within the operational amplifier circuits. So the in next slide we'll see the frequency response, that is why the bandwidth is not infinite. So here just see the board plot, open loop gain magnitude. So here we can see that now the gain is reducing as we are increasing the frequency due to the capacitance effect, and so we can't say that the bandwidth is infinite. So like this the corresponding the frequency response is plotted against the non-inverting amplifier. So the frequency response of this open loop gain can be written as AOL, that is open loop frequency gain, is equal to the AO, that is gain AO naught, divided by 1 plus of J F divided by FPD. So FPD is nothing. This is the dominant pole frequency, after which the gain will continuously decreasing if we are increasing the frequencies. And ft is the unity gain bandwidth, that is the also it can be written as fpd into a naught. So ft is, that is the unity gain bandwidth, will be equal to the product of the gain and the frequency of the dominant pole. And also 3 dB frequency can be determined by using this equation, that is fpd divided by a naught divided by aclo closed loop gain. And the gain bandwidth product always will be the fixed, and ACL can be determined with this equation, where if you wanted to find out the for the unity one, then the frequency will be equal to the ACLO FPD A naught divided by ACLO. Finally it will be equal to the the approximately it will be equal to the APD into A naught, which is also the equal to the f of t, as we saw in the previous slides. So that's all in this units. Second, apart from that, there are the various configuration like integrator and differentiators. We did not consider that configurations, but please you can go through that configurations that are also important, where we are using the capacitor in the feedback. If we are considering the capacitor in feedback, that is considered as the integrator, and if we are considering the capacitor in the input side, then it is considered as the differentiator. So please go through all those circuits that are important. In the next slides, we'll discuss for the unit third, that will be focused on the feedback amplifier and oscillators. Thank you for listening. If you have any doubts, please drop your comments. Thank you.